Good afternoon, everyone. We're starting class in 1 to 2 minutes time. Alright, good afternoon, everyone. And today's session, we're going to be finishing the topics of graph here with our shortest path topic, which basically illustrates how do we find the shortest path from one possible node to any other possible nodes in our graph. And then we'll move on to bit manipulation, which basically shows us how can we manipulate binary bits in a very effective manner using different sorts of operations. And we'll also be looking at how do we manually do these operations to begin with before we actually automatically do it in programming as well. But what you'll find is that when we move on to the bit manipulation topic, is that these tricks that we learn and these manipulation tactics that we learn with regards to how do we manipulate the bits will carry on into next semester when you start doing your introduction to microprocessors. So these techniques that you learn in the bit manipulation lecture are very handy to have and to look back on when you start doing the microprocessors course, because they will help you out quite a bit in regards to that particular course. So starting with our shortest path topic for today. So it is possible that given any example graph that you may encounter, you can find the shortest path between some source vertex and all the other vertices in the graph itself. And the name of the algorithm that makes this possible is referred to as Dijkstra's algorithm. It's very similar to the Prim's algorithm that we saw last week for the minimum spanning tree. And the similarity is that it's instead of how it keeps spanning for a minimum spanning tree, we keep track of the minimum distances once we cover all the nodes in turn, so you keep on finding and updating the shortest path required from the source node to all other nodes. And just to recap a little bit, remember a node also is referred to as a vertex in the graph. So let's say we have our example graph here, and we're going to start with node 0. And we're going to be required to find the shortest path from node 0 to all other nodes in the graph. So that means we need to find the shortest path from 0 to 1, 0 to 2, 0 to 3, 0 to 4, 0 to 5, and 0 to 6. And we're going to see how this algorithm that we saw, Dijkstra's algorithm, helps us find the shortest path in an effective manner. So the first thing that we need to do is that from node 0 to itself, it's just going to be 0 because that's our start point. And then for all other distances from 0 to the other nodes, we do not know what these distances are yet. So we formulate a list to say, okay, we don't know what's the shortest distance from 0 to 1, 0 to 2, and whatnot. And we represent all of these distances here as some very huge number. Conceptually, we use infinity here, but we know in programming we can't use that. So we either use some very huge number, or we use a negative number because we're only focusing on one directional distance. So we're not going to go forward and backwards with our sign bit as required. We also need a second list to make sure that we keep track of the nodes that we do visit so that we don't revisit them during this algorithm. And once we make sure that we covered each node in turn, we'll be removing each of these nodes here from the unvisited nodes list. That way we don't have to keep on searching throughout the entire list, optimizing our search and performing it even faster as we go on to successive nodes in our graph. So since we're starting at node 0, and node 0 to 0 is just basically 0, there's no set distance for this, because this is our start point, we mark this as visited so we can just immediately remove this from our list of unvisited nodes. So the red border that we highlight around node 0 means that, okay, we have already covered from 0 to 0, and now we need to cover, okay, from 0 to 1 in our listing. So in order to cover from 0 to 1 here, we also need to consider 0 to 2 because we're watching the edges that node 0 are connected to. So the two edges here are from 0 to 1 and 0 to 2. So we check these to see what would be the adjacent nodes to node 0. And we highlight the edges that are connecting to each of these adjacent nodes. Now, the adjacent nodes here are not immediately added to the shortest path. So the reason for this being is that we don't know in our initial search if this is actually the shortest path. But what we can do is that in our initial examination for this, we can actually update our distances here to match from 0 to 1 and 0 to 2 from our example graph. So if we backtrack a little bit, from 0 to 1, the edge weight in here was 2. And from 0 to 2, our edge weight in here was 6. So we can update this in our distance list. So once we update the distances of the adjacent nodes, we then follow these 3 steps here, to make sure that we cover our algorithm steps and to make sure that we don't do any revisits as required. So we use the shortest distance in our update there. So that's where we select the node that is closest to the source node based on the current node distance, and we mark this as visited. And we're going to add this to our shortest path. So node 1 had a distance of 2 from 0, and node 2 had a distance from 6 from 0. So we're going to use node 1 in this particular case. And we're going to add this to our shortest path as required. So when we actually start doing our shortest path here, we'll have node 0, the shortest distance from node 0 to another adjacent node, and we also highlight that connected adjacent node with its corresponding edge. So 0 here, the edge with weight 2 is highlighted, and node 1 here is highlighted as well. So because we have visited node 1 here as a result for our shortest path, and we have updated the distances as well, we also indicated with a red square visually here, say, okay, we found the shortest path, this particular node from 0. So this red square could actually just be a corresponding list here that can be Boolean flags that will be true and false in your program. Say, okay, when it's true, we have visited this square, and this is the utmost shortest path that we can get from our source node. So once we have that, we don't need to visit that node again in particular. And then we could cross off that node from our unvisited nodes list here as required. So then, after we do this, we kind of basically repeat the process, but we use the new adjacent nodes to find the shortest path to reach them. And we just keep on repeating this process throughout until we cover all the nodes and and we get all the required shortest distances. So in this particular case, when we updated our graph, nodes 3 and 2 are going to be adjacent to the nodes in our shortest path that we highlighted. And our shortest path so far would be nodes 1 and 2 that we need to consider. So we already had that distance from the source node to node 2, which was 6 on our list. So the only distance we need to update here is going to be from the source node here, 0, to node 3. And the question is, why is this distance going to be 7 in this particular case? So we're going to observe this in the next few slides. So remember, the highlighted path that we have here so far is going to be node 0, the edge with weight 2 here, and node 1. This highlighted path here represents our initial shortest path that we're calculating so far. The connected adjacent nodes from the shortest path here will be 3 and 2, which we saw in our previous slides. And we need to figure out, okay, from 0 to 2, what's going to be the shortest distance, but also from 0 to 3, what also is going to be the shortest distance. So in order to do this, we need to add all the weights from the source node to the target node that we're going to be doing in this particular step. So from 0 to 2 here, it's still 6. And then from 0 to 3, there are two possible paths, which could be 0 to 1 to 3, or 0 to 2 to 3. And we can see here, if we add the paths, 0, 1 to 3 will result in 2 plus 5, which is 7. And 0, 2, 3 would be 6 plus 8, which is 14. So that 14 here is going to be longer. So we consider the shortest distance possible instead. Similarly, we also consider node 2 here, because this is also an adjacent node that is connected. And we see that from 0 to 2 is 6. If we go 0, 1, 3, 2, that's going to be a very long distance, so that doesn't count. So we just consider only 0 to 2 here, and we update this distance here accordingly as well. So we update this distance here, which had 6, and we mark this as true with our red square, meaning that this is the utmost shortest distance from 0 to 2. And then for our next distance here from 0 to 3, we just update that distance here accordingly with 7, which is the initial shortest distance that we have. And we don't mark this as true as yet because we still have to analyze the other parts of the graph to make sure that this is the utmost shortest distance. So once these red squares indicating that these are the utmost shortest parts in our distance list are highlighted, we cross off the corresponding nodes here in our unvisited node list to mean, okay, node 0, node 1, and node 2 have been thoroughly examined, so we don't need to examine these anymore. The only nodes that we need to examine is 3, 4, 5, and 6 from node 0. And we just need to keep on doing this in order to figure out what's going to be the shortest paths for each one of these from node 0. So when we add this to our paths visually here, we only correspond this to where we had our finalized shortest distance, and we add this to our shortest paths in our graph itself. So we only consider node 2 here, which has the shortest distance of 6 from node 0, and we highlight that path accordingly with its corresponding node. We keep repeating this process for each one of these nodes in turn by actually watching these for the next corresponding adjacent nodes. So if we watch our graph here for our shortest paths, the next corresponding adjacent node that we do have from our end nodes here in the shortest path, which will be node 1 and node 2, the only corresponding adjacent node here is node 3. So we're going to have to figure out, okay, from node 1 to node 2, because we already have these shortest paths here, which one of these paths will give us the shortest path from node 0 to node 3. So we repeat the process as required from the adjacent nodes of our shortest path estimate to the new adjacent node that is connected in our graph. So there are two possible paths that we just saw. There was 0, 1, 3 and 0, 2, 3. And let's see how the algorithm here will decide which one is the shortest path. So we already had an initial distance that we updated in the list there, which was from 0, 1, 3 in our nodes, giving us 7. And that distance here was 5 plus 2. We had the other alternative, which was 0, 2, 3, which was basically if we were adding 6 and 8, and that gave us 14. And when we compare those distances, we see the 0, 1, 3 path here is shorter than the 0, 2, 3 path. So that's why we ended up with the distance of 7. The smaller distance will remain in the distance list from our initial estimate that we did in the previous step. And then we mark this off as visited because at this point, this is the utmost shortest path that we can have from our source node to node 3. So we actually put a red square here, and I know I didn't put it in. So let me just put that in on the slide. So we just put a red square here. See that in accordingly. Indicate, okay, we visited that. And that's the utmost shortest distance that we can get from our node 0. And once we know that is the utmost shortest distance, we cross off that node from our unvisited nodes, so we don't need to check it again. And we update our paths accordingly in our shortest path. So now we highlight node 3 here with its connected edges forming the shortest path as of. And the process keeps on repeating as of such to cover nodes 4, 5, and 6. Now, if we're considering from this point here what's going to be the new adjacent nodes from our shortest path, node 2 here connected to node 3, we don't consider that because we already estimated this, so we don't watch this anymore. The new adjacent nodes here from our shortest path connections would be node 5 and node 4. And we just repeat the process here for the adjacent nodes, and we keep on doing the estimates as accordingly. And that basically it's going to be the steps for our shortest path algorithm, known as the Dijkstra's algorithm. So for your homework, because I've already done 1, 2, 3, 4. I've done 4 of the nodes for you so far. Well, node 0 kind of doesn't count because that's just a self loop. So I've done half of the nodes. For your homework, see if you can find the shortest path using that same Dijkstra's algorithm and the 2 lists to find out what's going to be the shortest path from node 0 to 4, node 0 to 5, and node 0 to 6. By just repeating those steps that we just now saw. And once you figure it out, let's see if someone can post it up on the forum, and let's compare answers and see, okay, how did you actually went about doing this? And this is actually going to be some good practice for any of your further assignments involving graphs. Once you have to deal with your shortest path in particular, and you need to explain it in detail how you go about finding the shortest path using this particular Dijkstra's algorithm in order to establish it. Alright, so that brings us to the end of our graphs topic and the end of our shortest path algorithm. Are there any particular questions that need to be asked at this point in time? Feel free to ask them now. Yes, you can treat the weights as the distances from your source node to your target nodes, and you judge them using those particular weights to find the shortest path. Now, this shortest path algorithm is particularly useful, especially when it comes to things like GPS navigation, when you're trying to find the shortest path in between two successive cities or two successive destinations. And yes, this algorithm is a little bit simple because all it does is factor in distance. But when you start factoring other things like time and so forth and whatnot, the algorithm complicates itself a little bit more because now you have to actually have a math equation in the background to figure out how do we formulate a new edge weight based on our known distance and our known travel time to this particular point. So this is a good starting point for learning how to do GPS navigation between two successive points and what could be the successive paths that you can take by factoring these particular things. So the reason why we went through that other particular node was because how the algorithm operates, because you need to make sure that you cover all the edges that are possible towards that node to make sure that you have to make sure that you have considered all possible paths before you can move on to any other further adjacent node. So the reason why we did that revisit is that you need to make sure that all the paths were considered as a result. I understand why you're asking this, because we saw that it basically came off like a repeated step. And that's just a little bit of a flaw in the Dijkstra's algorithm, that you may end up getting some repeated steps as a result. But it can't be helped because that's just the way how the algorithm works. There are ways to optimize the algorithm to make sure that you don't repeat these particular steps, but it does involve using a little bit more memory to keep track of some of the paths. And at this stage, regarding how we're doing programming and whatnot, I don't really think you will encounter such a question, how to go about optimizing this, and that's a little more advanced and it requires a little more higher level skills in order to achieve this. That comes like if you're on the job and you already have some experience, they may ask you some sort of question like that from, for example, if you're moving from an entry-level position to a more permanent position, then you may encounter that particular kind of question. But for your purposes, you will not encounter a question like this as to how you can optimize your shortest path algorithm. Now, that doesn't to say that there are other shortest path algorithms that already do this. There are quite a few, but Dijkstra's is the best starting point for learning shortest path algorithms. All right, any further questions? Okay, doesn't look like we have any further questions, so that brings us to the end of graphs, and let's get to our final lecture for the entire programming series here, which is going to be bit manipulation.